In Chapter 9, Section 4, we're going to take our first look at an ellipse. We are still working on Algebra 2 State Standard number 16. The geometric definition of an ellipse, it'll help if I have the picture here, is the set of all points in a plane such that the sum of the distances from any point P to two fixed points, which we're going to call f sub 1, f sub 2, is a constant distance. Each fixed point is called a focus, so we have two of them. And when we talk about the plural of focus, we say foci. So that C has an S sound. It's not foci, not something you need to see your ophthalmologist about, but it's foci. And then R sub 1, R sub 2 are called the focal radii. So any point you select, the sum of the distances from that point to each focus is a constant. And we can watch a little movie illustrating that. So let's look at that movie just momentarily. In this movie, we have our two foci. And as we draw, and we have two focal radii, the sum of these distances are going to stay constant. As that red point goes around, we plot all the points on our ellipse. No matter what we have, the sum of these two distances stay constant no matter where that point is on the ellipse. So there's an animation, a virtual animation, seeing a virtual ellipse being constructed. Alright, and if you want to look at that again, you can do that in WinLab. And what I want you to do is have your packet out that I've printed out for you. And we're going to look at the information, which you can also find on the web if you don't have your packet with you, is what we're looking for when we see an ellipse in standard form. So an ellipse in standard form looks something like this. X plus or minus something quantity squared over some number plus y plus or minus something quantity squared over some number equals 1. It must also always equal 1. Now, from what we learned, we need to look at our packet, and the larger denominator is what we're focusing our attention on here for an ellipse. Now, be careful. For an ellipse, that's what we're looking for, but when we get to hyperbolas, we're not looking for the large denominator necessarily. But for an ellipse, the large denominator tells us which way the ellipse is going to be oriented. Since the large denominator is under x, and the x-axis goes left and right horizontally, then this is like an egg laying on its side, or a football, laying on the field. It's horizontal. And the center is going to be the opposite of the numbers inside the parentheses, just like we did with a circle if you pretended the denominators weren't there. So -3, +2 is the center. Now the square root of the large denominator we call a. And that tells us we're going to go the same direction as our ellipse, horizontal, left and right, from the center to find our two foci. B is going to be the square root of the smaller denominator, and we're going to go up and down 4 from the center, but that doesn't give us foci. Neither one of these gives us foci. It gives us vertices on the ellipse. Just thinking of the next thing that's coming up. So we're going to go left and right from the center to find two vertices on the ellipse, up and down 4 points from the center to find the other two vertices on the ellipse. So let's try to imagine these vertices in our head without having to plot them, because that's what we'll be asking you on your test. If you start at the center, go left 5, that would be subtracting 5 from the x value. Right 5, that would be adding 5 to that. Up 4, which is adding 4 to the 2, and down 4, which is subtracting 4 from the 2. That's what we're going to do. So to the left, -3 minus 5 is the point -8, 2. If we go 5 points to the right of this, -3 plus 5 is +2, +2. So those are my two vertices going left and right. And there are 4 vertices total for an ellipse. We're going to find the other two by going up and down 4 from the center. So up 4 from the center is 2 plus 4, or 6 for the y value, while the x value doesn't change. And then down 4 is 2 minus the 4, which gives us -2. Those are the vertices. Next, we want to find the distance from the center to each focus. And be careful about these formulas, because they're similar for ellipses and hyperbolas, but very different. For an ellipse, we want the large denominator minus the small denominator and then square root it. So 25 minus 16 is 9. The square root of that is 3. And the ellipse, the foci of the ellipse always go the same way that the ellipse goes. So if this ellipse is horizontally oriented and A is going left and right, C is always going left and right. So we're going to go left and right 3 from the center to find the foci. And let's do that in our head. Left 3 from negative 3 is saying 3 minus 3, which is, negative 3 minus 3, which is negative 6. Going right is negative 3 plus the 3, which is 0. So now that we've got just about everything mapped out, we've got to include eccentricity. Eccentricity for an ellipse is defined as C, the distance from the center to each focus, over A. And in this case, C is 3, A is 5, so the eccentricity is 3/5. We can leave it as a fraction or convert it into a decimal. All right, let's graph this with everything that we have. We've got our center. Let's just scroll back to see that that was negative 3, positive 2. We're going to go left 5 and right 5 to find 2 vertices. So there's a point left 5. Here's the point right 5. Here's the point up 4. And here's the point down 4. For our foci, we're going to go left 3, and from the center, we're going to go right 3. So I've color-coded them as red. With everything laid out, we just want to draw our sketch. Now, I was having trouble with Photoshop, so it's actually just the border of this gray shade. It's not everything in between. My ellipse is just the border line. It's just that line, not the entire portion. Now, an ellipse has 2 axes of symmetry, and so one goes through the center and the foci and the other 2 of the vertices. The other goes through the center and the other 2 vertices, and they are perpendicular to each other. One of them is going to be longer, and that's going to be called the major axis. One of them is going to be shorter, and that's going to be called the minor axis. Halfway across the minor axis is the semi-minor axis, which B tells us how long that is. Halfway across the major axis is the semi-major axis, which A tells us what that is. C tells us the distance from the center to each focus. All right, let's look at another ellipse. Go through all the same things we just went through. So here's our ellipse in standard form. Let's decide which way it's oriented. We look at our denominators. Larger denominator is under y. The y-axis is vertical, goes up and down. So this is a vertically oriented ellipse, like an egg sitting in the egg crate. The center is positive 1, negative 1, the opposite of the numbers in parentheses with x and y. A, the semi-major axis, is the square root of the large denominator. Square root of 36 is 6. A always goes the way the ellipse goes. So since the ellipse is going up and down, A, we're going to go up and down 6 from the center to find 2 vertices. B is the square root of 16, that's 4. And also notice that's under x, which goes left and right. So we're going to go left and right 4 to find our other 2 vertices. And let's do these calculations in our mind. Let's add and subtract. So if we add 6 to negative 1 to go up 6, that gives us the vertex 1, 5. If we go down 6, negative 1 minus 6 gives us a second vertex, 1, negative 7. If we go left 4, 1 minus 4 is negative 3, negative 1. And if we go right 4, we're going to add 1 plus 4. That gives us 5, negative 1. There's our 4 vertices. We need to find the distance from the center to each focus. So the large denominator minus the small denominator, 36 minus 16, which is 20. Square root of 20 is 2 square roots of 5. And that's approximately 4.47. We'll just round that off to the nearest tenth and call that 4.5. And C always goes the same way A goes, always goes the same way the ellipse goes, so that we're going to go up and down 4.5 from the center to find the 2 foci. So let's do that calculation in our head. Up 4.5 is negative 1 plus 4.5, or 3.5 for the y value of that focus. Down 4.5 is negative 1 minus 4.5, or negative 5.5. Eccentricity is still C over A. In this case, that's 2 square roots of 5 over 6. and that reduces to the square root of 5 over 3 if we leave it as an exact value. Some books will ask you and some teachers will ask you for a decimal equivalent. We're going to try to go with the exact values. All right, remember our center is 1, negative 1, so let's start plotting our graph. 1, negative 1 is our center. The semi-major axis is going to go up and down 6. So there's the point up 6. There's the point down 6 from our center. There's 2 of the vertices. We're going to go left and right 4. So there's our point left 4 units from the center. Our point right 4 units from the center. Let's find our foci, which are 4.5 up from the center and 4.5 down from the center. All right, let's draw an oval shape through the blue points. And again, it should not be everything inside. I was having trouble with Photoshop, so it's just the border here. We don't shade everything inside. This would be the situation if it was our equation less than 1, or less than or equal to 1. But it's just the border outside. We have a major axis, we have a minor axis of symmetry, 2 lines that you could fold the graph on and both sides would match up. Again, the longer one, the major axis, the shorter one, the minor axis. Alright, and just to review then, eccentricity, it measures the flatness of an ellipse when compared to a circle. For an ellipse, we're always going to get a value between 0 and 1, not including 0 because that's a circle, not including 1 because that's a parabola, but somewhere in between. So an ellipse, eccentricity is greater than 0 and less than 1. We calculate that using the formula C over A. And that's our first look at ellipses.